Hello, everyone. Welcome to another binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Today we have a Chrome bug, a hypervisor bug, and a pretty neat iOS info leak. Before all that, though, we'll let Z cover Spot the Vuln.
Yeah, so this week's Spot the Vuln, well, I guess not this week, I've been leaving them up for a couple weeks here, is another one that we have used before. This one, I believe it was somewhere around episode 99 when we had Bastian Gruber on. We were kind of talking Rust, so had this Rust-based issue. Um, and I think this is kind of a good example of where or how Rust can actually be nice for spotting vulnerabilities, but the fact that there can still be vulnerabilities in Rust code. Key thing there is like you do still see this unsafe, so that tells you something weird is going on here. Why is that unsafe? Um, and if you take a look at this code, it is kind of a Rust specific issue. It has to do with Rust and object lifetimes. Specifically how, inside these curly braces that each curly brace set, I should actually mark a matching set here. Each set basically represents a lifetime. So a variable declared inside of there will be freed when it goes out of scope. So you've got the curly braces as your scope. Once code goes out of scope, it'll free any of the variables that are scoped to just that area. So in this code, starts off this sign function doing whatever. Sets up this let p equals match. So basically, whatever it matches on in here is going to be the value that gets assigned to p, and that can either be a none if it matches on data being none. It's just going to use a null pointer. If there is something, it's going to it's going to create a new bio slice um, out of that data, and then take the pointer of it, and that'll be assigned to p. And then we get down here, and it's going to call like convert p, CMS sign p, whatever those are doing doesn't really matter, but it's going to pass in this same p value. The problem is that p is going to get the value, or is going to get this pointer value from this bioslice that is newly created inside of this scope, and that is just inside of that match statement. That new bioslice is scoped inside of there. So as soon as you leave this statement and you get to this unsafe, you leave that match statement and that bioslice gets freed. You're still storing the pointer in P, but it has actually been freed at this point. So usually Russ is going to be like, hey, this has gone out of scope, and like it's not going like you do it, but use unsafe and you end up getting that access to P. So this is one of those cases where unsafe is definitely telling you something might be going on, something can go wrong here, some assumptions can be violated or whatever, but you still need to understand the code in order to really spot the vulnerability. So it doesn't just make vulnerabilities really obvious, but it does give you kind of insight into there might be something wrong here and limits where you kind of need to look and where you need to verify things are like working as you would intend. So I do like this vulnerability. It is something we used before, but I think it's a really good example.
And it's been a while since we've seen like Rust
This is the
vulnerabilities
only
on
Rust
the show.
vulnerability that we've done to spot the vuln on too. But yeah, we
No,
also
I
haven't
just mean in
covered.
general.
Yeah.
Yeah. All right, so we'll get into our topic. So leading off, we have a V8 exploit, and I'll let Z get into this one as well.
Yeah, and this one is actually originally written in Korean, so I have the Google Translate up here for um, readability because I cannot read Korean. Unfortunately, that also means this post can be rather hard to follow. I think part of that is like they're writing this, I think, assuming you have a reasonable amount of insight about how some of the Chrome V8 exploits work. And also just, the fact that it's being translated, sentence structure. Like, for example, this first sentence here, V8 is a Boolean object. I don't quite think that's what's going on here. That's what it appears like, but whole is this V8 object that is what they refer to as an oddball type. Oddball types are just like the predefined sort of values, like true or false would be in there. A Boolean being true or false is defined as like the oddball type. undefined is an oddball type. The hole is another one, which just represents like an empty space, like an array. So if you delete an element from an array, that deleted spot will be replaced with the hole. Um, I think I was talking with you just before the episode started, Spectre, that you mentioned like WebK uses similar terminology for the hole. So I'm assuming this is kind of common within the browser or within kind of browsers to do this.
Yeah, so it's kind of a tricky case to handle, right? Because when you're offering control over arrays to something you'd consider untrusted, which the JavaScript engine would be, you can't just allow JavaScript to be able to access like free elements from an array and then try to access that memory. Like you have to handle weird cases like that. So that's where the terminology with arrays with holes comes from, is that there's sections of the array that are not owned by that object,
yeah.
basically. So yeah, it's one of those tricky types that the browser or tricky scenarios that the browser has to deal with. So they came out with this type. Yeah.
Yeah, and as you can kind of guess, like this is kind of a specialized thing, specifically as you're saying, with JavaScript. It needs to kind of do this. It needs to have something representing this sort of thing where, your average application probably doesn't. And so you have the hole. And it comes out with the fact that this whole object is not exactly a normal type. Like it is an oddball object, but it's also a little bit different in that they don't want like user JavaScript to be able to use this. So like it should come out like if you tried to do anything, if you managed to get some JavaScript object that like pointed to the hole or was like got it as a JavaScript object, it should come back as like an undefined or an undefined value. And that's where the issue comes because the hole isn't like a well-defined object, it would seem, and it doesn't have this or it doesn't have a proper implementation of the two number type. So if it tries to convert into a number, it doesn't really have any good or doesn't have an implementation to do that. I believe is how they kind of explain this here. And that creates a problem when it comes to optimization. Because they have this simple function here, this function test. And what ends up happening is they just go in here, let index equals number, so converting it to a number. And one of the options there is it can, in some cases, it has a ternary expression here that it's either b for whatever value is being passed in, and then can either return the whole on true or if it's false, -1. So the problem kind of here with the whole object is when it tries to optimize this, it's going to do a range analysis. It's going to try or value range analysis, and it's going to try and figure out what ranges can this index be. And in other codes, they get into like they'll use that index value that's being returned to actually index into an array. Um, and so it's going to do this value analysis to see like can it go out of bounds, or I don't think it's quite that sophisticated, but what it will do or what it can do is look like, is this a small number that's going to go beyond ideally boundaries or whatever. It can optimize that check, but if the possible value range is small enough, it'll actually I am getting ahead of myself a little bit, so let me return to that in just a moment. Touching on the incorrect optimization first, because the whole object, so we're jumping back to that ternary expression, because the whole object doesn't have a two number defined, the optimizer running through here sees the only possible value of index as being -1. The whole doesn't return like a not a number value, like it doesn't get that from the two number. It doesn't. The way they explain it here, at least the way I'm understanding, is it doesn't have an implementation of two numbers. So I do apologize if I'm getting some of the details wrong, but because it gets that value back and doesn't actually get a number back, thanks, Kate, there's nothing going to happen there. So the only possible value we can go forward with is -1. And of course, the range is going to be pretty small then. It's going to be low values because of that. So it can do whatever other operations, multiplication, addition, but it's just based off of that -1. It won't get any other value. And so because of that, the range, or because of that, either accessing the array via index, it'll still do all the bounds checks properly and there won't be an issue. as of 2019. Before 2019, using the array indexing, so that's your square brackets for those of you who can't see, doing that indexing into an array, if the value was proven to be small enough using the range analysis, it would just drop the boundary check and optimize that out so it would just be faster to access into the array, because in theory the value should never like exceed the bounds. They added in a or they basically forced the boundary check to always exist when you're doing array indexing. However, they also have this method for an array, or prototype method for an array, called at, which lets you access a specific index. And that didn't get the same patch in 2019. Seems like that was basically left unpatched. It could still optimize out that boundary check. And so combined with the whole, it having this wrong interpretation of the value, so combined with that, plus if you use this array.at method, they could basically trick the optimizer into creating code that doesn't do the bound check, and then actually provide a value other than -1, or get a value other than -1 used to get an out of bounds array access. Which in my mind, like, this is all very browser specific. Like, you're not going to run to this exact case. You don't have a lot of code, doing an optimizer. But I kind of want to shout this post out more on just that edge case of like a type that isn't supposed to be used. Um, being not completely implemented or not properly implemented. As being kind of the introduction of some sort of bug. Yeah, in this case, we're getting that out of bounds access. And this does go more into the exploitation, which I'm not even going to really go into, because that is definitely not my area, and I don't think I would do it justice. But I thought that core vulnerability of having this random, sorry, I'm just looking in chat, XCD80, oh, this is a bit similar to CV 2019-0567, where optimize can cause a type confusion. I'm not sure if I'd call this one like a type confusion exactly, because it's not the
I know what he
optimizer.
means.
Okay, yeah,
Because I was gonna actually say something very similar. I was just waiting for you to finish what you were gonna say, because it does have like a type confusion type feel to it. It's not exactly a type confusion, but the way it works, it's sort of the same methodology, if that makes sense.
I guess it starts with the type confusion. Like, the optimizer itself has a type
Yeah.
confusion, which then leads to it optimizing wrong.
Yeah, exactly.
I think that would be maybe the way I'd work type confusion in there. I didn't think about it that way, but I mean, yeah, it is kind of that type confusion going on at the optimizer. But I don't know. I thought this was a fun bug. We talked about dropping this post before the episode, and I'm like, you know what? I don't like I can't follow it super well, but the bug itself is still kind of cool to me.
Yeah, but as you say, with the browser, it's these types of optimizer bugs are very specific to the unique problems that browsers have to handle. So it might not be as transferable outside of the browser space, but it was still pretty cool.
Not specifically. Like, I mean, you also don't run into like a JIT and an optimizer in too many cases outside of browser. But at the same time, you do run into these edge cases where just certain types or certain objects aren't expected to be passed through. They're not expected to be seen in certain ways. Like, that concept can still apply, although that is a very high level take on this.
Yeah. And XCD80 mentioned it's not type confusion, but it's the optimizer. Yeah, I mean, the optimizer just, it's where the meta has moved to for finding browser vulnerabilities, just because it's so complicated. There's so many layers to it. And yeah, there's just a lot of like unique, like JavaScript. The JavaScript engine already is really complicated. Like, you're dealing with people being able to run code, but then the optimizer thrown in is just like a whole nother layer of complexity. So it's where a lot of research has moved to, and it's why on a lot of hardened device configurations, the like JIT and the optimizer is just disabled outright, because when you start trying to drop like guardrails and things like that, then like optimizing out code, how do you make sure you don't optimize out security checks, right? Or in this case, making sure that the type that you're using has a method that's implemented properly So
Yeah, and to be clear, I'm not entirely sure if it's just not implemented because while saying that, they do also show this, operator type to number being undefined, which kind of makes me think, oh, maybe it is returning an undefined, but I recall them talking about um but, like that it should be undefined and the fact that it's not. So there, like I mentioned at the start of this one, like I did have some issues trying to follow it exactly because of I think just the language and translation barrier.
yeah, and the optimizer especially, like I've done some browser research, but getting into like the optimizer and Chrome specifics, I'm not really up to speed on all that either. So yeah, I can't really clear up too much of that confusion myself. All right, so we can get into our next blog post. So this was a post by Satoshi Tanda on how I find Microsoft Hypervisor bugs as a byproduct of learning. Um, and this was a bug that came out of sort of not properly intercepting a specific machine state register. So when you're doing like getting into a bit of background, when you're doing virtualization, one of the things you have to be careful to protect whenever you're virtualizing and you don't trust the guest is you have to intercept things that talk to the host hardware that might do dangerous actions. And one of the most well-known surfaces and one of the largest surfaces is machine state registers, which for those who aren't familiar, they're basically special registers you can write to with the WR MSR and RD MSR instructions, which will take an MSR address in a register and then a value, and either read or write that value. And these MSRs can hold lots of different types of information and configuration. So it can hold like configuration of whether or not paging is enabled, write protection, virtualization. You can also have like the page table base address registers, things like that. So there's a lot of like pretty sensitive registers here for the host. So the hypervisor has to intercept reads and writes to various sensitive MSRs to ensure that the guest doesn't have free reign over them. And the way that's typically done is the hypervisor will establish an MSR protection map, which the CPU will reference whenever accesses are made to the MSRs. And if it's an MSR that's marked that should be intercepted, it'll do a VM exit. The hypervisor will handle that, and it'll decide whether or not to actually commit the write or to do any changes on it before the write's committed, or to just outright deny it. One of the dangerous MSRs in this case, that was detailed a bit in a previous blog post as well, was the hardware feedback interface, or HFI related MSRs, particularly the IA32 hardware feedback pointer MSR, which would be used to hold the physical address of where to write performance information on a reset. So if the hypervisor lets you write this MSR unintercepted, like it was in this case, you could give it, say, a hypervisor physical address to get this feature to corrupt hypervisor memory, and that's pretty much exactly what happened here. Now, it's worth noting that exploiting this is not as trivial as it might sound at first. For one thing, you have to be in a position to be able to write to MSRs, which means you're going to have a compromised guest kernel or something. And then on top of that, this HFI structure only gets populated on a system reset. And on a normal boot, the kernel will write to these MSRs with its own values. So how they took advantage of that here, or how they say it could be taken advantage of, is by leveraging sleep states. So like S3 or S4 for sleep or hibernation, which is not a complete shutdown, but it's basically a sleep mode that'll cut down the clock speeds, suspend things to memory and whatnot, saves context to storage, like long-term storage, or whatever you would want to call it. There's a lot of stuff that goes into it. It's a whole like other mess. But the whole idea there is you skip a lot of the initialization that would be needed on a hard reset. And in this path for S3 sleep states, the MSRs would only be written to conditionally, which they say they can skip. I don't think that's really elaborated on too much in the post, but the fact is they can just skip the kernel writing its own values to those MSRs, which then gets them the hypervisor write on like an S3 resume. And with that, you can target pretty much anything you would need to break the hypervisor, even if you don't control the data that's being written. There's a lot of data in the hypervisor that's super critical, like nested page tables and things like that. So you could just smash like a page table entry or some other critical piece of data and break the hypervisor. So
As you mentioned the condition for this, I found that a little bit on the write-up. So they do, I feel like, kind of skip a reasonable amount of information here and really just focus on here's what the issue is. But yeah, as I was reading this, it's like all that's really said is I realized that in the case of resume from S3 or S4, the kernel conditionally wrote the MSRs and that condition was controllable. By controlling the condition, I could avoid the MSR reinitialization. It's like, I would have liked to have known, like, was this conditionally, like, you just set a flag? Was this conditionally, like, in how you did it? Like, I don't know, but reading it just felt too vague to me, like, suspiciously vague. So I'm wondering if there's even like another vulnerability, something related to that they're not trying to mention.
Yeah, I'd
I don't
like to
know what
try
it
to
would be, but sorry, go ahead.
Well, I was just gonna say I would try to speculate, but I'm not as like I'm fairly familiar with hypervisors at this point and like the boot process, but not as much with the boot process from S3 state. Because when you're like booting normally is way easier to handle than booting from a sleep state. Like there's a lot more code that goes into that. So because of that, there's any number of things I could think that would conditionally allow skipping the MSRs. Um, like
Yeah,
even
like
just
it.
like the sleep state phase number at some point or something like that. But yeah, I can only like vaguely speculate.
Yeah, like I could imagine things for it. I just thought it was suspiciously vague to mention a condition with no information about the type of condition. That said, it could just be how they chose to write. Like it doesn't have to be anything odd going on there. Just they don't want to go into those details. What matters is what we're saying. It could be skipped, but it stood out to me here.
But yeah,
Um,
part of the reason I wanted to cover this post too is a lot of the time when we talk about hypervisor issues, it's going to be some piece of code in the hypervisor that's for extended features like VMware and having input being paravirtualized or things like that, or like a hypercall. You don't really see it too often where it's an MSR that wasn't protected properly. Although MSRs are kind of hard to secure, like there is a ton of different MSRs. I mean, this isn't as much of a problem for Microsoft, but like a lot of MSRs are also not really documented that well. Um, so it can be easy to miss one, and that's just seems to be what happened in this case.
yeah, like they kind of call out fact that I think there were 80 some, yeah, 81 MSRs were writable, and he just went through. He kind of calls out that maybe there aren't as many eyes coming on this as they would have expected. Looking into attacks that come from root against the hypervisor because as they mention down here, if any researcher had inspected the MSR bitmaps for the root partition, they would have found this issue. Um,
Well, see, but that's part of where I was getting into with the lack of documentation. Even like I tried looking up this MSR a little bit, and I was able to find a little bit about it in like the Intel manual, one of the 900 pages. But like the MSRs are not like outside of the really common ones like the EFR extended features MSR and things like that. They're not really documented that well, at least in the public documentation. So even though like somebody could have, I could see how somebody might have looked at the bitmap and just not thought that this register was important, or maybe not even knew the name of this particular register.
I guess I'd have expected it to be done by Microsoft, honestly. So this is
Yeah, Microsoft in particular, you would kind of expect it, but like outside researchers, I'm talking about.
yeah. No, I kind of this is kind of tying in where you're talking about how we don't see a lot of like the hypervisor bugs that haven't been like the features of like whatever, like VMware, VirtualBox, or yeah, whatever. Like that haven't been that area. And another thing, we haven't seen a lot of issues in like Hyper-V and Microsoft's hypervisor system. Um, and so this one kind of stands out for that. And yeah, I just kind of had the expectation that Microsoft could have had that knowledge and somebody should have looked over this. Like that feels like something that would have been part of their process. Because I understand they do take the security of Hyper-V fairly seriously because of how they're using the whole platform. It's used across Windows, of course, as part of like the virtualization based security that they talk about here, but it's also used throughout the Azure cloud. So like they have a serious reason to invest in it. So it just surprised me. Again, it's something that could have been overlooked. It could be, like I said, just not documented well enough to realize how it could be abused. Whoever looked at it didn't have that knowledge. variety of reasons there. But it is kind of the thing where, you get the eyes on, you find it, and hypervisors, like in terms of outside researchers, I don't think it's one of the more popular targets. I mean, browsers are obviously popular. Um, Operating systems at this point are popular. And I think with that, because of Microsoft having kind of that more deeply embedded virtualization based security, hypervisor will get more popular out of that, I imagine. But
I agree.
yeah, hypervisors feel like they're a little bit like really undocumented at this point, like just in general, not a really good understanding of it. And therefore, that's also just a reason for not as many eyes coming on it.
That's what
Uh,
I think it is. I think part of it being obscure and undocumented, as well as it just not being a super juicy target because of the high level of access you need to be able to exploit it. Like it's, I don't really remember the last time you've ever really been able to exploit a hypervisor from user space or something. You generally need to get guest kernel, which then you're talking about a chain of potentially 2 or 3 vulnerabilities before you can even exploit it. And in some cases, you might not even need to care about the hypervisor if you're just going for like data only type attacks, right? So, because
the
virtualization based
cloud,
security
though,
will protect, yeah, the
that's the
cloud
big
and
one.
things like that. But even then, like the cloud, um, again, it's kind of obscure and there's not really a lot of good information on it, so it's hard to break into, right?
Yeah.
Um, so yeah, I think it's a combination of just not being a super juicy target at the moment and also being somewhat obscure. But I do agree. I think it will become more and more relevant over time as it's being relied on more for things like cloud and consumer security as well.
Yeah, and one of the other thoughts that they have in here I want to bring up is actually their first thought, the verify your assumption. This is something I tend to say a lot, but when you're testing something, you're looking at an application, even if you think there's no way they're going to make this mistake, it's usually worth it to just try it and take a really quick look. And, you just try and come up with that test case. It's just going to be a really quick, dumb test case to be like, yeah, okay, they took care of this. But actually checking it and making sure, because I've seen it a ton where people are like, no, they wouldn't have done that. That's not how you would implement this feature, and therefore kind of miss over a vulnerable area. And we've had other bug reports kind of talking about how, they overlooked something for a while and then maybe went back and did this. It's like, just if you're assuming something, just give it a quick test. It might be a waste of time, it might not, but just verify your assumption.
Yeah, always a good reminder to have. All right, so continuing with some Microsoft stuff, we
Just before
also
we jump
have.
off, sorry, I don't know if we mentioned, but they did get a $2,000 bounty. I don't recall hearing you mention that, but maybe you did.
Yeah, no, I didn't mention it. Yeah,
So
good
they
show.
did get a bounty for this issue, also.
Yeah, which actually I was a little bit surprised that it was that low. Like typically with Hyper-V bugs, like their payouts are larger, but I guess in this specific case, because of like the lack of control over what's being written and whatnot, and the fact that like being able to write MSRs is a little bit tricky, especially when you have the virtualization based security, like HVCI, protecting you from patching kernel pages and stuff. Like the whole idea with HVCI is that you can't get your own code running in the kernel very easily. So you would have to do some like ROP chains and stuff to get MSRs going. So that could be a reason why I paid it a little lower too. But yeah, I was a little surprised it was at 2,000, but good shout. They did get a
Yeah,
bounty
I
for it.
just pulled up the Hyper-V bug bounty program, so I was just going to see kind of where it falls, and it actually falls under the minimum value. They say, these qualified submissions are eligible for awards from $5,000 to $250,000, whereas this one was just 2,000. So it's actually falling outside of it. And yeah, there definitely are some challenges. I would feel as though this could be one of those cases where so Microsoft does have kind of better pay if you provide a better report. And so in this case, like their report couldn't have really provided a lot of detail on what was going wrong besides just you could write this, like no
Well, there might
actionable
just be some
internal.
other
And
circumstance that I'm
then
not aware of.
Well, and then the exploitation of it would be fairly tricky. So they wouldn't have been able to provide like a stable proof of concept or something, things like that could kind of bring it down. But I was hoping to see a table here, but I just see, yeah, denial of service, like low denial of service payout range. I guess these aren't like the exact values that you're going to get paid, but up to that. So I guess 2,000's kind of still. fitting, I guess, but it does just feel a little bit funny that they mentioned the awards being 5,000 as like the starting place, and this one didn't quite make it. Sarsek mentioned, I've gotten more for an XSS from Microsoft. Maybe it's a typo and was actually 20,000. I believe their screenshot here, yeah, it's is actually from the Windows, like what they mentioned there, and eligible for a reward of $2,000. So I guess unless Windows actually had the typo there, but then they also make mention of the 2,000. So if they were actually paid 20,000 and kept repeating 2,000, I don't see that one as likely. um,
Well, here's something I missed too, which I should have called out a bit earlier. This was an issue that was specific to Intel processors, so it wasn't like a globally hittable issue on all like x86 devices. Like AMD CPUs, as far as I know, wouldn't have really been vulnerable to this. So
like
that could
wouldn't
be
have
a
had that
factor too.
MSR.
Yeah, I believe this is specific to like an
Okay,
Intel
that's
feature.
yeah. I mean, I guess the MSRs are a bit more manufacturer specific, but
Which is another thing that complicates things with MSRs, and is something we should mention as a, you know, to be charitable to Microsoft, is that you also have like AMD and then Intel, and they have different feature sets, and you have to play catch up with both of them. And it's not super fun. So
yeah, fair enough. That is a good shout. Um, I think they actually mentioned here where in submitting this, they weren't even sure if this would be worth it, like if they would view this as a vulnerability, given that an administrator, you need that admin level access, could disable like virtualization based security just with BCD. I think that's supposed to be BCD edit, but it's EIDT, or I'm just confused.
I think it's a typo. I think it's supposed to be
Uh,
BCD edit. Yeah.
that sounds like the more familiar command, but there's always BCD edit. Okay, I'm not going crazy. But yeah, so they do mention like an admin could just disable it. Nonetheless, I feel like this might have an impact elsewhere beyond just the VBS that maybe they're not aware of, or maybe not. 'Cause, I mean, they don't really call it out as specifically impacting Hyper-V, but the VBS is, as they call it, as like this para pass through VM setup. They have a link kind of explaining the VM setup a little bit. Yeah, para pass through hypervisor design. Um, just in terms of how it works, and I think Hyper-V is more of the full fledged setup. So perhaps it does an impact there, but still, I mean, they got a bounty for it. And actually, that is probably a fair thing. I was looking at the Hyper-V specific bounty program and not the VBS, so that is another aspect of it that could impact payout.
Yeah. All right. Continuing on the Microsoft train, we also have a Windows issue, and I'll let Z get into it.
All right, so this one is kind of an older issue. It is dealing with a CV from 2021. And this is impacting kind of like cloud file sync. So if you've ever, on Windows, like Windows 10, you'll notice in like the file explorer, there's like a OneDrive option, and you can have like your OneDrive accessible as if it were a local drive. And that sort of thing is done using these file filter drivers or cloud file. What do they call it? Cloud Files Mini Filter Driver is what they refer to it in here as. Basically, the driver is going to implement like transforming just a stub file or just like a placeholder file that maybe has a few bytes of a header, transforming that or syncing it with the actual file when requested, but only maintaining like these placeholders for a while. It's going to deal with all the complexities of making remote files available through the local file system. And so part of how that works is that they will set a reparse point, kind of associated with the file, and that can include a little batch of somewhat arbitrary data. It does have to include like an appropriate tag and some stuff there, but you'll have like the actual data buffer, and you can supply the data length for that. And then the tag itself is supposed to basically just correspond to a specific driver or something like that, and has to be reserved, and like you have to go through, or as I understand, you have to like go through Microsoft to get a tag that you can use. Or oh no, so I was looking at them. They seem to have several like A, B, C, D, E, F type tag and 0 through 9. So it seems like maybe some get to reuse them or something, but like they have a few reserved. Nonetheless, in order for to reach code, you need to have a specific tag, and it needs to be the tag that this vulnerable driver is expecting. But ultimately, like a user on the system can make the call to set this reparse data. And so coming into the bug, it is reading. So the inputs to this are coming out of that reparse data buffer. So it's not really like an argument you're passing in. It's associated with the file, and then you trigger into the other functionality. So it is a little bit weird in that sense. I'm just looking for the code here. So they ended up doing patch diffing on this one. Just saw this bug got patched. But here is the vulnerable code. And effectively, it is grabbing some size. Now, this is the size value from, or this is the data length value, I believe, from this reparse data. So it's just grabbing that size. Kind of goes through here, does an allocation using that size, and just does a +8. And a little bit later, it's going to try and decompress the buffer. So that is like the data attached to it. It's just going to go ahead, try. It's in this LZNT1 format, which doesn't really matter. What matters is that like the buffer itself will start with a little bit of metadata inside of it. That kind of defines how it's to be read. So contain like size information. It'll contain if it's actually compressed or if it's uncompressed data, and some information like that. But what matters at this point is really just that you have this allocation, and that is using the size that's controlled and just does the +8. And then because it's going to place like a header at the start of that, when it's passing into the decompressed buffer, it's going to just pass in that allocated buffer +12, so just a little bit ahead of it, leaving a little bit of room, and to compensate for the fact that it's adding, or it's not at the actual start of that buffer, it'll, when it passes in the actual size here, it just subtracts 12 bytes from it. And that is the problem. That subtraction. So if you set the size of the buffer, again, that is just a controllable value. That reparse data length. So controllable value. If you set that size to something small, like 0, it's going to go through all of this, allocate some size +8 bytes, and then it's going to decompress, and it's going to go +12, and then it's going to do this subtraction -12, and that is going to underflow, which means it's going to be a very large size value. Of course, when RTL decompressed buffer is actually doing the decompression, it's going to read the data buffer. Again, that data buffer is hacker controlled coming here. That's what's going to be decompressed. It's going to read that, and it'll get the size out of that. So this is a nice case where the underflow gives you this insanely large value because it's negative whatever. It's going to give you this really big value, but it's not copying that value. That is just uses the bounds limit. So as big as you want in your actual buffer, it's only going to read, I think they call it out in here, it's only going to read like 4,000 or hex 4,000 bytes from that buffer. So there is some restriction on like your sizes, but you can get a fairly large write out of that, or fairly small writes out of it if you don't want to actually overflow too far. So it is a pretty nice primitive in that you control the size that it's actually going to write, and your actual allocation is always just going to be this very small allocation, so you get it to underflow. In terms
Nice
of
scenario to be in for sure.
yeah, I mean, so often when we deal with both overflows and underflows, you end up in this case where you have to find some trick to end the copy early, or you need to do something. Otherwise, you're just going to copy too much data. So yeah, this is a nice place to have that underflow happen. They do get into exploitation. I won't cover all of the exploitation, but because these objects, because it's that really small allocation, that's just going to end up in the Windows low fragmentation heap. It's going to end up in a bucket. They mentioned here of the hex 20 byte objects and 10 bytes of, or it's going to end up, sorry, in this bucket of a bunch of 20 hex 20 byte objects. The challenge there is there's also a header on these of about 10 bytes, so each thing can only actually hold about 10 bytes or hex 10 bytes of user data, which isn't a lot of information if you're wanting to get a primitive by overflowing an object. Like, you don't have these really nice, big, complex structures to overflow into within these really small buckets. And so the way they decided to try and exploit this issue was actually by first just spamming to try and fill up all of the currently available buckets inside of the low fragmentation heap. Hoping that if they filled those up and while at the same time allocating some variable objects, the Windows notification foundation feature, I forget what the F stands for, but WNF state data, it's a relatively common primitive object. I'll talk about in a moment. And token objects, basically spamming those or spraying those, hoping that they'll fill up all the low fragmentation buckets, and they'll end up getting like a new variable size segment created, so that they'll have a low fragmentation bucket right beside a variable sized subsegment. They kind of show in the picture, hoping for that, so they get their overflow somewhere in one of these LFH buckets, and they'll just be able to overflow into the variable size segment, hopefully corrupting one of these state datas. And those state datas contain there were two sizes now, and I unfortunately in my notes didn't. Here we are. The allocate size and a data size. So they're basically just overflowing with hex 1000, hoping to corrupt the allocate size and data size. And the WNF state data, if you Google it, you'll find other people talking about trying to exploit this, because it's just a generally useful object for trying to get a relative read-write primitive. So they end up going for that, changing or creating a much larger allocate and data size. So they'll be able to access relative data that's adjacent. Since you're spamming that object with the token object, they'll be able to manipulate a token object that is right next to, or ideally right next to one of these state data objects, giving them a easier, I guess, win state from there. So yeah, on a whole, like I said, as a bug, comes down to like it's a little bit of an obscure input point. Although if you're working with the these mini filter drivers, probably not as obscure as I would think, but yeah, I think it's a pretty fun bug. It is a little bit older, and on that note, I will also shout out that if you want to get more information just about the core bug, this post is mostly about the exploitation. But on the core bug, there was a ZDI post back around when this was actually disclosed. And this goes in, I think, in better detail over how to actually kind of get through to the vulnerability itself, and a little bit easier to understand, I think, than the Star Labs blog. Not that the Star Labs blog is like bad or anything. The ZDI post just had kind of more information in there.
I was half wondering if we might have covered the ZDI post, but it was in July of 2021, so it would have been during our summer break, so we probably didn't. And I don't remember having covered it, so.
Yeah. No, I mean, since it was in summer, I don't think we covered it. If we had covered it, I probably would have dropped it from this episode. But yeah, it didn't feel familiar either. I mean, we have covered some things with the cloud filter drivers, but yeah, I hope we didn't cover this one already.
Oh well, I mean, we covered so many topics, it's hard to remember sometimes, like, what we even covered a few weeks ago, never mind 2 years ago. So I would, I'll give this a pass. So moving into some Apple research, we have a post by Dataflow Security, or DFSec, which is a pretty funny and wild bug in XNU due to improper handling of the fault address or FAR register, particularly when it comes to clearing it. So the idea with the FAR register in ARM is when you trigger an exception, the CPU will go to the exception vector table, handle it. Those exceptions can be synchronous or asynchronous. They talk about that a little bit in the blog post, but it's not super relevant. What matters here is synchronous exceptions. And synchronous exceptions can happen on like instruction or data aborts when you pass invalid addresses, alignment faults, anything like that, or even just like page in faults. And when a fault occurs, the faulting address is copied into the FAR register for debug information, copying it back to the struct, the task struct. And that address, depending on where it faulted, can be like a kernel or a user address. And in particular, when you try to access a freshly mapped piece of memory in user space that hasn't been faulted in yet, or in other words, it's not backed by a physical page, when the process goes to access that memory, the fault will be caught by the kernel, which will then page in the physical page for it, which you might have heard referred to as pre-faulting before, which is where you just write to some area of memory to get that memory paged in. The thing is, the kernel page address is copied into the FAR register, but the FAR register is only updated on certain types of exceptions, and it's not cleared after the exception is handled. So in particular here, a breakpoint debug instruction will not update the FAR register. So when the core state is copied into the thread structure, it'll copy that old stale kernel pointer and the FAR register into the stack, and that's your info leak. It's pretty simple with how it works. It's just kind of abusing the fact that this register is not cleared across different exceptions. And it's pretty rare you see bugs like this. I have seen like kernel info leaks through not clearing registers before. I've seen one in FreeBSD where like certain registers that were used for syscalls and whatnot weren't cleared, and kernel addresses could leak that way. But it's not something you see very often at all. So yeah, I mean, pretty nice as far as iOS bugs go, in that it's fairly easy to understand the gist of it. They do go into some of the specifics of, how the exceptions work and the virtual memory system architecture, which in its own right is a good reason to recommend this post. Like they do a good job of explaining how that all works.
Yeah, they did a
But
good
yeah, like
job with the background on this one. Like, just this post alone is enough to just understand the bug. You don't have to go read, like, how, some of the registers work and stuff. They did a good job with that.
yeah, it's very nice. Often when you see these types of bugs, it's assumed that the reader has already knows how all these things work. So even if you're not intimately familiar with kernel or XNU kernel, you can read through this and understand what's going on pretty well. So yeah, nice quick cover and a really cool bug. And it's the first blog post that's been done by DFSec. So um, yeah, they said on Twitter, like, after 3 years or whatever it was, we finally got a blog post out. So yeah, and it's a really good one.
And maybe another 3 years for the second post.
Hopefully not. All right. But with that covered, we can get into our shoutouts. So up first for shoutouts, we have this just really neat website that was put out called the Chromium Money Tree browser. And the whole idea with it is it shows you a tree view of the Chromium source tree, but with the bounty amounts that have been paid out for issues in that area. So um, I mean, it's kind of funny to just look at and be like, which subsystems are the most vulnerable? And, they're as expected. Like, the highest payout is in the browser, a lot of UI based bugs, and like the DOM rendering and all that kind of stuff. But yeah, I mean, not only is it just kind of neat to look at and be able to see where a lot of the issues are, but it can be a super useful tool too. You can get a pretty quick view of the landscape of where issues are being found, and on the flip side, where people might not be looking as much, right? So just a really cool idea. Unfortunately, it's probably not an idea that can be applied to a lot of other targets, because Chrome is a little bit unique in how open they are with their bounties and publishing the amounts. So that's why they were able to get the data together to put this website up. But yeah,
Getting the
but
amounts
Chromium
and
is a good
having
benchmark of the security landscape in general too. So it's still like very valuable, even if you're not necessarily full time into the Chromium research.
it's also just generally kind of interesting to see it broken down like that, even if you're not going into the Chrome research. Just, that's interesting that they had, like, as I was just kind of scrolling through here while you were talking, I noticed they had like an extension there with Dice Web login. I think it was. That's not the yeah. Dice Web sign in interceptor delegate. Like, there's a $5,000 bounty in that. Like, just a little bit surprising to see like some of just the random things in here. It's a cool sign. I think with a lot of other projects that would be hard. Like you said, in terms of the bounty amounts actually being visible, but also associating the bounty with commits and with like
Yeah,
specific code is not something that's very easy to do on most projects. Like,
yeah, and
even with
I
Linux
mainly
being pretty open, I don't think you'd be able to really replicate this super well.
No, not without a ton of manual effort, I don't think. But yeah, I mainly called out the monetary amounts, but they also have the number of reports in red next to it too. So you can do some interesting analysis with comparing the bounty payouts with the number of reports and whatnot too. If you want to like really dig down into it, just a lot of cool information there. And the second shout out we have is from Synactive, and it's how to voltage fault injection. So we don't really cover like hardware attacks too much on the show, particularly because we don't have a huge depth of knowledge in that area. I am trying to build knowledge in that area, but it's definitely not something that I'm super confident on. But this is a post that is targeted towards people like myself who are interested in getting into fault injection. So they talk about some of the various different types of fault injection you can do, like clock glitching, optical fault injection, EM, and the trade-offs involved with all of them. And then they go in depth on voltage glitching. So they basically take you through glitching a Arduino Uno with a Chip Whisperer Lite. One thing I wish they did do is they also show you on an oscilloscope what the whole idea with glitching is. For those that are watching, you can kind of see they have this oscilloscope graph of the voltage. They have it steady, 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 and then towards the middle, they have where they inject their fault, where the voltage drops really low and then goes really high and then settles back to a steady state. I wish they talked a little bit about like finding good oscilloscopes or being able to narrow down the parameters you need for oscilloscopes for doing these types of attacks. But nonetheless, they take you through like the methodology of voltage glitching and basically glitching a simple script that you would upload to the Arduino to cause something to happen, like skip a loop or something like that. So it is a really I always like shouting out posts that go into like fault injection and hardware attacks because it is a bit of a tricky area to get into, not only because there's not a ton of information out there about it, but also it's just it's not super intuitive. You're basically causing the CPU to not operate within its like recommended conditions, and what happens is completely unpredictable. So it's not super easy to practice either. It's a lot of trial and error, but getting some insights and tips and tricks and whatnot and how it works. Yeah, I think this is a cool post for that. So if you're into the hardware stuff, I would recommend checking out this post and maybe following along with it too, for your first attack, because that might be what I end up doing actually. But yeah, with that out of the way, that's all the topics that we have for today. So Z, unless you have any last minute thoughts, we'll wrap it up there.
I will actually bring up one thing. Rudimal says, I guess most would do as long as they sample fast enough. And you were kind of talking about the oscilloscope before the podcast, so I'm not sure if you'd want to reply to that.
Yeah, so there's a few things with oscilloscopes that like I wish I knew a little bit more on uh what kind of parameters you need when you're going for a particular target. So the sample rate is like the key one. So, you know, if you're trying to target a chip that's running at 200 megahertz and you have a 100 megahertz scope, you're probably not going to have a good time. But on top of that, you also have the the speed, I should say. But you also have the sample rate on top of that, so you can have like a 1 gigahertz, 10 gigasamples per second scope. And I don't know exactly how those factors tie into what you would need for a particular device, and that's kind of the thing that I wish this post went into a little bit more. And I would be curious on getting like a. I mean, maybe it's not a hard science. It could be depending on the target and how much noise there is and all that kind of stuff too. But yeah, it's a bit tricky to tell what scope you would need, and it's easy to spend a lot of money on a scope. Like the higher speed, higher sample rate your scope is, the prices quickly jump. So you want to be able to accurately estimate what you need without going like super overkill and spending like $10,000 or something, because that's not what I want to do.
I mean, just to be safe, spend like $10,000 or $20,000. You'll probably get something good then.
All right, good tip.
That's the entry level. That's your starting point.
Perfect. Yeah. All right, but yeah, with that out of the way, that's all the topics we have for this week. So thanks goes out to all of you for listening. If you want to go back and check out past episodes, you can find recent ones on Twitch and all of them on YouTube, Spotify, Apple Podcasts, and more links on Anchor. Feel free to join the Discord and follow us on Twitter. Links for those are down below or in the chat. And also feel free to leave some feedback there on our potential format change for the podcast. We're thinking in the new year, maybe moving to a record-only format, or at least not a scheduled stream format. So we'd be curious on some feedback on that. And with that said, we'll see you next week.